Okay. Welcome everyone, and thanks for joining us today. This is the latest installment of our data and machine learning webinar series. My name is Marc Phoa. I'm a client engagement principal at DiUS, and I also look after the AI and machine learning practice. And that means I'm responsible for sales and building our internal AI capability. I'm here with my colleague Shahin Namin, our principal machine learning specialist. He'll introduce himself when he gets started. But before we do, in the spirit of reconciliation, DiUS acknowledges the traditional custodians of country throughout Australia and their connections to land, sea, and community. We pay our respects to their elders past and present and extend that respect to all Aboriginal and Torres Strait Islander peoples today. Now, a bit of housekeeping for those who are new to these sessions. There will be time for questions at the end of the talk. So if you have any questions, please go to Slido and enter that code there, or you can scan the QR code you see over there as well, and that should take you directly to the page. We'll also put the link to the chat, I believe, as well. This presentation is being recorded, so when we're done, we will share this with everybody. Yeah, if you want to look at the slides, you can see that through the presentation itself. Now, in terms of the agenda, I'll start with a bit about DiUS, and then I'll talk briefly about what we're seeing in the market and what we're hearing from our clients. Shahin will then step in and provide a quick recap of Gen AI, where he'll cover generative versus predictive models and explain the role of foundation models and LLMs. He'll then dive into how organizations can adapt these models for their own needs. And we'll walk through some sample case studies, including some of the tools and platforms we're working with. And of course, we'll leave some questions to the end as well. Okay, for those who don't know DiUS, we're an Australian technology consulting company. We've been around for 19 years and have about 150 people across Australia and New Zealand, from engineers, software, data, cloud, to delivery leads, QAs and experienced designers. And this allows us to form cross-functional teams when solving problems for our clients. And this is particularly important when we're building ML products. We're quite unique in that we have a deep in-house expertise, I guess, across digital data and devices, as you can see with the diagram over there, which includes machine learning and IoT and how to bring that all together. Today's talk is about is in the data machine learning series. For those who have followed us over the last couple of years, you would have heard us speak about various machine learning applications, how to get your models into production, data readiness for machine learning and related topics. We've got a lot of machine learning powered solutions, including a lot of traditional predictive models such as forecasting, churn prediction, recommendation systems, and some more unique scenarios combining AI with IoT devices. Now, that's quite a bit of ground to cover with new technologies emerging all the time. An important part of what we do is we explore a lot of these tools as part of our system of innovation. The tools, platforms, and practices that are emerging, essentially in order to help our customers apply them to their own problems. And Gen AI is no different. We've been running our own experiments and applying Gen AI in commercial context for our clients, and sharing those experiences is essentially what the focus of the talk is today. So, what are we hearing from our clients? Firstly, we've all heard about how ChatGPT has caused an avalanche, I guess, of avalanche of interest and conversation, a lot of media hype, both positive and negative. And there's so many announcements from tech companies, cloud providers in particular, around new models, tools, and platforms. And that's making it increasingly more difficult to wade through all the noise. ChatGPT has created greater awareness, and the flow-on effects, I guess, has made AI much more accessible to the general public, employees, and businesses alike. With all that hype, we're seeing our clients compelled to do something, not only because their staff are using these services, but also the need to explore it in order to compete, really, when you're baking it into your own internal processes and products as well. So the barrier to entry has been lowered, but what we're seeing is the expectations and the competitive pressures have increased as well. So what are we seeing from the organizations we're speaking to? They're exploring both Gen AI and traditional or predictive models, from forecasting, churn prediction, and the like that we mentioned earlier. they're asking us whether to use Gen AI or Predictive for their particular problem, especially when you can choose either. In some circumstances, we're seeing customers daisy chain a series of models. So that's a combination of predictive and generative in order to solve their particular problem. In terms of text and versus image, we're seeing most of the interest in the text and natural language space. Lots of customers are using it for improved search, and often combining that with a conversational interface as well, so chatbots. Also attribute extraction, report and document generation are other common examples. From an image perspective, we're seeing it mainly used for photo correction rather than in the creative space. And that's only based on the type of, I guess, organizations we're working with. Shahin will cover the technical details around these, and will include examples of both text and images. What we're also seeing is organizations getting started with easy to access services like ChatGPT and Google Bard before they invest more time into exploring other options that will allow them to customize the solution and give them greater control. At this point, we might take a bit of a pause and launch a quick little poll, actually. So this should pop up on your screen, and you should see a few options here. Essentially, what we're trying to understand is, where are you on your journey? You might still be learning about what's possible with Gen AI. You may have identified a problem and looking to get started, or you're already building some existing solutions with it. We'll give it a few moments as people are filling that in. How's that looking, Erin? Oh, it's not working. Okay, sorry. Erin's just told us it's not working. That's okay. We can do that a little bit later. So, apologies, everyone. Before I do hand over to Shahin, I wanted to share something we've seen from AWS. It's something they use to segment their customer base, and we found this to be quite useful. Starting from the bottom there is what we call the consumer group, or the consumers. This group is largely using pre-trained models to build their applications, and they're usually accessed via APIs with very little customization involved. Then when we move up, that's what we call the tuners, right in the middle there. This group is customizing those pre-built models for their own unique application or data set. So rather than consume it just via an API, they're customizing and hosting these models on their own cloud environments. We expect, I was hoping to see that from the poll, but we're expecting to see, I should say, we expect most organizations we work with to be either consumers or tuners of models. And we suspect most people on this call will also fit under that category. The last group is the top group there, providers. Now, this includes the likes of, OpenAI, Stability AI, Meta or Facebook, cloud vendors like Amazon. So they're training Gen AI models from scratch and making them available for tuners and consumers like ourselves. These organizations would have access to enormous resources, from data, compute people, etc., to build these models and essentially do a lot of the heavy lifting for us. Now, I also wanted to quickly align this to a diagram that many of you would have seen in the past when we've spoken about traditional predictive AI. Now, consumers, again, are typically users of services, so ML as a service. Examples are Amazon Recognition, Comprehend. There's a whole bunch of others from other cloud providers as well. They're really easy to use, but might not give you the performance that you need if your data or problem is unique. And then you've got tuners, which are equivalent to those who are building custom predictive models, which is essentially what DiUS specializes in. You can achieve much greater accuracy and performance. There is greater complexity, and you'll need some specialized ML skills to achieve the outcomes that you want. Now, Shahin will use a similar diagram to show what this looks like for generative AI. And on that note, I'll hand over to Shahin.
Thank you, Mark. Hi, everyone. I'm Shahin Namin, Principal Machine Learning Consultant at DiUS. And from this point on, we'll be starting from a recap of our previous talk, which was the generative AI, the foundation models and large language models. Just a very quick introduction and an overview of what we talked about there. That is also available online for free on YouTube, so you can look it up and listen to that talk if you've missed it as well. So when we talk about machine learning applications, we can categorize them into predictive versus generative. So predictive approaches and applications are the traditional AI applications where you have a single correct answer to your problem. As an example, you might show an image of a cat to your model, and the model would tell you that that's an image of a cat. So there's a single correct answer for that problem. These are usually very narrowly trained, so they are specifically trained for a specific problem. The data set has been limited, and they are good at doing that specific task. Whereas in generative AI, we are talking about applications where you have more than one correct answer to your problem. As an example, if you are using a text-to-image Gen AI model, you might set as input a text, which is a sitting cat, a sitting black and white cat, and the model might come up with many, many different variations of cats, and all of them might be correct. So this is an application of generative AI, and we usually see that the purpose of using generative AI models are to generate data. And the underlying models, machine learning models, are called foundation models. So foundation models are the models that are trained on very, very large amounts of unlabeled data and some labeled data. The input of these models can be text, images, different modalities, audio, and so on and so forth. And you can use these models to adapt them to your own problem. And this is what we will be talking mostly in this talk. But what we've seen in practice is that these generative AI models can even solve predictive AI problems. And the two modalities that are the most common ones these days are text and image models. And even with a small amount of data, you might be able to tweak these for your own problems. Some of the applications that you can do with these models are natural language processing, predictive tasks, as well as generating images and generating text, and so on and so forth. So when it comes to natural language processing, these foundation models are called LLMs, or large language models. So basically, you have many, many different implementations of large language models by different companies such as Google and Amazon and OpenAI. You see a list of these here. The input of these models are called prompts, which are basically a set of text that you pass to these models, and you usually give them some instruction. You say, this is the specific task I want you to do, or this is the question I have. I want the answer for that question. So these, the output of these models can be of many, many, of course, it is always text, but it can be applied to many different problems, such as generating new content, summarizing the text you have, translating, coming up with some code, question answering, and so on and so forth. What is important here is that with adaptation of these models, you can get them to do some specific tasks for you. And usually the natural language processing tasks are well suited for large language models. Similarly, we have visual foundation models. So these are the models that take as input an image or video, or similarly, they might give you an output, an image or a video. And basically, what we will be talking in this talk applies to both large language models and visual foundation models, but we will be talking about large language models and use those terms mostly in this talk. So when it comes to the different types of models that we have for visual foundational models, you You hear Stable Diffusion and Midjourney a lot these days, but of course, there's a lot more different models that are available out there, and the number of models are increasing every day. So generally speaking, when it comes to foundation models, they might take as input or output different modalities. It might be text to text, which is the LLMs. It might be image to text, text to image, and so on and so forth. And again, almost the whole content applies to all these models, although there might be slight variations in how you would apply them. Right, so from this point on, we will be talking about how we can adapt these large language models for your own business problems. So as Marc mentioned, we have providers. Providers are the companies and organizations that have a lot of resources. They are specialized in generating and making such large models. These models are very expensive to train. So this is basically not what we will see in practice. We see that these models are prepared and are ready, and we can actually use them and adapt them to our own problem. But regardless, what providers do is that they follow a three-step procedure in order to prepare a large language model from scratch. The first phase is called pre-training, where you have a very large amount of text data. It might be the internet, it might be Wikipedia or other data sets, and you ask the model to try to predict the next word in the sentence. And you go through your data set and try to make your model learn basically the structure of a language. After this phase is done, you go and fine-tune this model for different tasks at the same time. So this is called fine-tuning, and we will see that we will do a bit of that for our own adaptation later as well. But in this phase, providers have a lot of data sets of different sorts, which are always, let's say, for language models are text to text. So it might be for different applications, for summarization, for translation, as an example, and so on and so forth. And they try to train and tweak these models in such a way that they can do these tasks after they are trained. And the last phase is reinforcement learning with human feedback, or RLHF. So this is when you ask the model to give you the answers, you give them to human labelers, ask them whether that was a good answer or not. And based on that, you go and tweak your model further so that what the model gives as answer or completion is aligned with how humans would respond to a question. One important point here is the size of these models. There has been a paper that does some investigation on the model sizes and the data sets called Chinchilla. And the idea is that the models, most of the large language models are already over parameterized, which means that they are bigger than required if you look at the data set they have been trained on. But what is important here is that because these models are very expensive to run, so after you deploy that, the infrastructure would be very expensive. So you want to make sure you use a model wisely, and you don't always want to go for the largest model possible, because that means that you will be spending a lot more money if you just factor in the size of the model. So that is something to have in mind, although we are not generating these models ourselves to start with, and we are usually talking to consumers and tuners. So when it comes to adapting large language models to your own problems, there are 4 different techniques that are widely used these days. If you are a consumer, the assumption is that probably your machine learning knowledge is not very deep, or you might want to experiment very quickly with these models. So the first technique that you might try is prompt engineering, which basically you try to tweak the inputs that you send to the model and try to get the model to give you a good response. And it's an iterative process. So you go and tweak the inputs again and again until you get it right. Next is retrieval augmented generation. So you use this technique when you have a data set that you want to ask questions or retrieve information from, and you don't want to go and tune the model, or you might not even know how to tune the model. But this is actually a very good technique, and we see that it works really well in practice. So this is a very quick overview of what these building blocks and techniques are, but for the rest of the talk, we'll be talking about each of these building blocks in more detail. Regardless, if you are in the tuners category, that means that you have some machine learning knowledge, which means you can make use of that knowledge to increase the performance of large language models for your own problem. And of course, the complexity of tuning these models will be higher than how consumers would interact with these models. And lastly, similar to providers, we can do reinforcement learning with human feedback, and we'll be talking about that as well. So let's look at every building block and see when you would use that, why would you use that, and what are the best scenarios and the best cases for them. So prompt engineering is first. This is when you go and change the input of the model or the prompt that you send to the model in order to achieve the task you have at hand. So you usually start experimenting with LLM using prompt engineering. Basically, you go and change the prompt again and again until you get it right. And this is usually suitable for applications where the model has seen the data in the fine-tuning phase when the provider have provided that model. So it might be something such as sentiment analysis or question answering on the information that is available generically on the internet, summarization, translation, and so on and so forth. So what matters here is that usually prompt engineering gives you some answers, but it might not be accurate enough for your own problem. So if you can tolerate some incorrect answers, you might even stop here. Otherwise, you might go and explore other more complicated techniques in order to get these get better results for your application at hand. So one approach that is used with prompt engineering is called in-context learning. So one approach is just to tell the model, this is my problem, give me the answer. So assume that this is a sentiment analysis problem, which means you have a sentence, you want to know whether it is positive or negative. It can be a review of an item, or it can be feedback or anything like that. So in zero-shot inference, you go and say, this is the sentence I want you to calculate the sentiment on, give me the answer. So usually what we've seen in practice is that if you are choosing a smaller large language models, they usually don't do really well in zero-shot inference. So you might want to use one-shot inference or few-shot inference that we'll be talking shortly. So in one-shot inference, you go and embed an example of the question and answer or prompt and completion in your input prompt, and you pass that to the model. So as an example, you go and say, hey model, if I was going to give you this sentence, I'm expecting you to give me the sentiment equals negative. So that's an example that I provide to you. Now I have a new review. Tell me what the sentiment is. So this is called one-shot inference. And one reason that you might want to use that is you might be dealing with smaller models. And we've seen in practice that smaller models work better if you provide a few examples or even one example to them. And of course, similarly, you can provide a few examples to your model, and this is called ViewShot Inference. And we've seen that this might result in better performance, but the number of prompts that you would embed in your, the number of examples you would embed in your prompt is limited. So what we've seen in practice is that if you are going to give more than 4 or 5 examples to the model using few-shot inference, the model wouldn't increase its accuracy from that point onward. So that's the limitation that these models have, and also the size or the size of the text that you send to these models are usually limited, and sometimes you get to pay extra if your prompt is longer. So you might be a bit careful about using few-shot inference, and again, more than 4 or 5 examples wouldn't help the model as much. Next technique is called retrieval augmented generation, or RAG. So this is when you have some additional information that you want to provide to the model, but you don't want to change the model or tweak or fine-tune the model. So when would you use that? When you have an internal knowledge base or some other data sources, and you want to limit what the model gives you to that knowledge base. Or you want to go and ask the model about the information that is available in there. So it's a very good technique if your knowledge base is changing, because you are not fine-tuning the model. It's actually very easy to go and incorporate your new data set into or change data set into the currently seen data set that the model had been exposed to. And it is suitable for problems such as summarization, sometimes search and retrieval. So go and ask a question about the data set that was available, give me the answer. And of course, you don't need to tune the model in this technique. So how does that work? It's a two-phase process. In the first phase, you go and index the data. What you do is that you go and partition your text data set into smaller partitions. It might be sentences, it might be paragraphs, it might be overlapping parts of the text. And then for each of these partitions, you send them to a natural language processing model that converts them into a vector embedding, which is basically a set of numbers that represent the text and the information that was available in that text. And then you go and store these vector embeddings in your vector database. A vector database is a database that can store and work with a vector of numbers. And one good feature of vector databases is that it can give you similarity. So assuming that the items that have the same or similar content will end up within the proximity in the vector space, you can go and ask, give me the relevant information or the information that is similar to the information that I want to point out. So we are making use of this this capability of vector databases. So how does it look like in the inference time? So once you do the data indexing, basically you've copied and kept the vector embeddings of your corpus or knowledge base in your vector database. When it comes to inference, let's say that someone asks a question, you go and use the same model as before to convert that into a vector embedding, and then you go and ask your vector database to give the relevant information that actually is similar to the question that I've asked, or within the proximity in that space. Once you have that, basically you found, let's say, a few examples where the information is relevant. You go and find the text and then embed them into your prompt, and then you ask the question. So basically, this step is to create the prompt and embed the information from your knowledge base into your prompt or input of the model. And then you go and ask your large language models to give you an answer for your own problem. So this is very useful because it requires some software engineering and implementation, but it's actually quick and easy to be implemented. So you can actually use this technique in order to come up with a question and answering of your own data source or Q&A on your website, as an example. So next technique is fine-tuning. From this point on, the assumption is that you have some deep machine learning knowledge. We try to simplify that, but still there are some technical terms here that hopefully are understandable. So the idea here is that you are going to change the weights of the model using your own data set. And when would you use that? When we see that in-context learning or prompt engineering doesn't give you enough performance for your own task, or RAG doesn't solve your problem. As we saw, RAG is a specific technique that is suitable for some specific applications. So one other reason that you want to go and fine-tune your model is because your domain is very specific and you use unique and specific terms, for instance, finance, law, medicine, and other other industries and disciplines. So these are the examples that you might want to go and fine-tune your own model. What happens when you fine-tune these models is that the models usually lose the capability to give you good answers for other tasks that they have been trained on. So you are basically limiting these models to your own task. You get better results. It might be one specific application or task, or it might be just a few. You still use the same model, but basically it gives you pretty good results on your own task, but it actually loses the capability and the memories it had that it was using for giving you good answers for other tasks that is not in your data set. And of course, the assumption is that you have a labeled data set relevant to the problem at hand. With model tuning, one thing to be aware of is that large language models are actually really big in size, and that adds to the complexity of hosting these models, and it becomes very expensive very quickly, and you might not even have the right compute resources and memory resources to host these models, or actually to train these models. That's even more computationally intensive. So there are different techniques that you use. The technique you see on the left is called quantization. Basically, what you do is that you go and rather than using a 32-bit floating numbers, you might use other types of numbers, which might be a 16-bit or even an 8-bit number, like an int 8 number. What we've seen in practice is bfloat16 is extensively used in practice these days. The way it works is that the first bit is reserved for sign of the number. The next 8 bits are for the exponent, and the last 7 bits are kept for the precision of the number. So we've seen in practice that this works really well. And if you've heard of FLAN models, which are usually Google models, these are the models that have used BF16 or BrainFloat16 before training the model, actually, or during the training of the model. Next technique that you might use is hopefully you have access to some GPUs, more than one GPUs, and you might be able to use distributed training of these models. One technique that is being used extensively for tuning of these models and training these models is called fully sharded data parallel, which is an approach that is proposed in 2019, also with the name zero optimization. The idea is that they have gone and looked at what would consume most of the GPU memory when you are training a model. What they realized is that optimizer states constitute the larger portion of the memory. After that, the gradients, and after that, the parameters of the model that you need to keep in the GPU memory. So the zero optimization goes and shards this memory and copies that and splits that into different GPUs. So basically, when you are using multi-GPU, you are losing the speed of training these models, but the trade-off is that you can train a much larger model. So there are 3 different stages in zero optimization. Stage 1 goes and splits the optimizer states into different GPUs, and it keeps a copy of the gradients and parameters in each GPU. Next step is stage 2, where you can go and split and shard the gradients among your GPUs. And stage 3 is parameters, where you basically split the whole memory GPU among different GPUs that you have. But if you use stage 1, 2, 3 together, we see that the reduction is linear with the number of GPUs. So if you add a new GPU, let's say, and you only had 2 GPUs, so that the model that you can train after that can increase by 1/3, as an example. So it actually linearly reduces the amount of memory required per GPU for your model. Next technique is basically parameter efficient fine-tuning, or PEFT. So as I mentioned, one problem with tuning your model is that the model forgets doing other tasks. So you might sometimes need to copy and train different versions of the models for different tasks. But when it comes to the GPU memory problem, one technique that is used even in computer vision with the name of transfer learning is that you might freeze parts of your model and fine-tune a subset of the model. It might be the last or the deepest layer of the model, or it might be just a few layers. So you can use the same techniques with large language models. And of course, when it comes to these techniques, you are still sacrificing a bit of performance. So if you had the opportunity to go and fully train the model, although it is very expensive, you would get better results. But usually the amount of performance loss is small. Second technique here is to keep your model frozen and add some layers or components to your model and try to train them. Two different techniques that we see are commonly used these days are LoRa and prompt tuning, which we will be talking next. So LoRa, or low rank adaptation of large language models, is actually a very handy technique, which is very fast in terms of the training of the model, and also the amount of memory required is much lower. So in this case, you go and freeze the weights of your layer as an example, but you go and try to come up with a matrix that is of the same size as the layer weights when these two matrices are multiplied together. So these are two lower rank matrices. So the number of parameters in these two matrices are much lower than what you find in the actual layer weights. And therefore, the amount of memory requirement will be much lower. And you've frozen that, fixed this, and you've basically trained these two matrices. And you just go and add these back to your frozen weights after you go and train these models. So usually the rank of these matrices are 4 or 8, or among along that number. So it's not a very big rank that you would use in practice. And we've seen that if you just go and applying this technique to self-attention layers, you still get very, very good results. So this is called LoRa. It's a technique that is being used more and more because it is actually fast. It is simple to implement, and it's actually the amount of memory requirement will be much lower. Second technique is called prompt tuning. In this case, you just go and add a set of parameters to the input of your model, and you try to train those parameters. So basically, you are appending these soft prompts to the actual prompt. So the way the models work is that when you are giving a text to the model, each of the tokens, or let's say words in these in your input, gets converted to a set of numbers that represent that specific word. And then these are concatenated together and are passed to the model. What you do in prompt tuning is that you add a set of other embedding or vectors to your prompt, and you try to train that for your own problem. And if you have more than one problem in hand, you just go and train these specific soft prompts for each of those tasks, and you just use them. Usually 20 to 100 tokens or words that are appended to the prompt is good enough to get a very good result. Next is reinforcement learning with human feedback. So when would you use this? Firstly, what is it actually? So it is actually to get some feedback from your human labelers or some humans, and try to tweak your model in such a way that these models work better and are aligned with what humans prefer. So when would you use that? This usually comes after tuning. So if you've tuned your model, you might want to go reinforcement learning with human feedback. This is a little bit more engaging compared to tuning. So you might think about whether you want to do that or not. So when would you use that? You want to improve the responses with human feedback. So you want to make sure that what the model will give you later is aligned with what a person would give as the answer. And also you want to maximize the relevance of responses. So you want to make sure your model doesn't give something out of the blue or doesn't hallucinate for your specific question, as an example. So this is a good reason that you want to do RLHF. And lastly, you want to minimize the potential harm. As an example, you don't want the model to give out sensitive information, some hateful or harmful content or dangerous information. So RLHF will make sure that your model can give the right answer, which is not aggressive, which is not harmful or hateful. How does it look like? So it is a two-step process. In the first step, which is called reward model preparation, you go and ask your large language model a question. So you pass an input prompt, you ask LLM to generate different answers or completions for that prompt, and then you pass them to a human labeler and ask the person to rank these answers based on their preferences. And you might give them instructions and say, rank them based on how hateful they are or whether they are relevant or not, and so on and so forth. Once you have the rankings, you go and use these ranks in order to train a reward model. So what this reward model does is it's a model that gives a number or a score for each prompt and answer. Once you have this model, you can use it in the next phase. I have to mention that sometimes these reward models are ready, or you can find an off-the-shelf model that does this for you. So you might find a model that can capture how hateful a text is, as an example, and use that in practice. And this is the most complicated and most expensive part of RLHF as well. So next step is to, assuming that you have your reward model, you go and do the basically reinforcement learning feedback loop. You have an input prompt, so basically a question that you ask your large language models. The large language model comes up with an answer. Then you try to evaluate that model using your reward model. You get a score, which is basically your reward, and you use that score to provide feedback to the model, whether that answer was good or not. And you try to tweak the model and tune the model using reinforcement learning techniques. The technique that is used here and the reinforcement learning feedback loop that is used here is of the form policy optimization in reinforcement learning. And one very good algorithm for that is commonly used is called PPO, or proximal policy optimization. Right, so let's say that now you've gone through these steps and you've come up with a model that does the task well for you. So what are the considerations when you go and deploy the model? So what are the LLM ops considerations here? Most of these come from the fact that model sizes are very big, and therefore the latency of these models are also very small, because the amount of calculation that goes into giving a response is actually very high. So the techniques you might use might be of the form that goes and tries to shrink the model. So you might use some techniques like quantization, as we talked about. You can do post-training quantization. You would lose a bit of performance again when you do this, but still it might, because the amount of money that is spent on your infrastructure after this phase will be lower, it might be worth it. Distillation is another technique where you go and basically train a model that looks at what the actual model that was trained would give you, and then tries to learn from that. And it might be a smaller model. And then after this step is done, you can go and use the distilled model, which is a smaller model. Some of the frameworks that are available makes it easier to deploy these models, and sometimes it makes it even faster, and it changes the model structure a bit as well. And you see some of these frameworks here. And of course, you can use some software engineering techniques like caching in order to come up with much faster responses. I had to mention that LLMs are not very good at reasoning, but there are some techniques that are that are investigated and are used these days if your problem is a reasoning problem. So one of them is called chain of thought. In this way, in this technique, what you would do is that you go and say, if you give me that question as a person, these are the steps that I follow. These are how I would go and solve this problem. You give it as input as part of your prompt to your large language models with the new question as well, of course. And you go and say, basically, you're asking the model to follow the same procedure to come up with the answer to that reasoning problem. So there are a few other techniques here. If you are going to take actions according to your prompt, as an example, if you have a chatbot that is going to book a hotel or something like that, you might want to use one of these techniques. So the first one is called PAL, or Program Aided Large Language Models, which was proposed in 2022. The idea is that you get your model to write some code according to what was passed to it, and then you pair the model with a language interpreter. Once the large language model came up with the code, you can pass that to your code interpreter and get the code interpreter to do some specific tasks for you. So an example of that might be that the model might generate some SQL code for you according to what was asked, and based on that, you might send that SQL query to the next step, which is basically a database, and get the answers and show the answers back to the user. A second technique is called REACT, or synergizing reasoning and acting in large language models, which is also proposed in 2022, late 2022. The idea here is that you might basically instruct the model to go and do some specific tasks. So you come up with some terms that are specific, and you add them to your prompt. And once the prompt is parsed, if those terms are found, it might call an API, or it might replace that prompt with what it gets from a database, and so on and so forth. And that way, you can get LLMs through this framework to call APIs or do some specific tasks for you as well. So one thing that is important here is that you want to make sure you avoid adversarial responses, and you might use some guardrails around what the model gives you. So these are to make sure that the data or the result is relevant, or even the question that was asked from the model is relevant. And you might use the actual model to self-criticize the answer it gave you, or you might use a different model that might say, oh, this is a harmful answer, so don't pass that to the end user, as an example. So you might want to make sure that you have these guardrails in place when it comes to productionization of these models. And lastly, cloud providers provide different solutions, different Gen AI solutions that might make implementation much simpler. An example of that is Amazon SageMaker, or Jumpstart and Bedrock that are provided by AWS. Similarly, GCP has Vertex AI, GCP Garden, and Generative AI App Builder. The other cloud providers are similar. So you find different services that they provide in order to simplify these techniques. Right. So let's look at some case studies quickly. So we will be talking quickly about 5 different case studies here. One of them is in the prompt engineering that we ran for Programmer. 2 of them are in the RAG scenario, and we will look at 2 image examples when we did fine-tuning for our clients. And these are all implemented on the cloud, and they're making use of different models, as you see on the screen. So this is an attribute extraction experimentation that we are already exploring for Programmer. Programmer provides project management software for interior designers and architects. And also they've used predictive models in order to dedupe their product catalogs. But now they've been exploring Gen AI to help them extract information from the website. So as an example, let's say that this is the content that you have. You want to make sure you can automatically extract some of the information that is available and matters to Programmer. So we came up with an implementation of a feature extraction on GCP, and it's using Google Bard's model. And basically, you pass the URL of your item to this website, if you like, and then it can come up with different attributes that it can extract from that website. And what we've seen in practice is that basically it is a prompt engineering implementation, and sometimes it doesn't work really well. Sometimes it hallucinates and comes up with a wrong price, especially if it's not available, or the description might not be exactly what you find on the web page, and so on and so forth. Next is Finder GPT. So this is a RAG example where you can pass your knowledge information or data set to this website. It goes and does the indexing, and then you can come and ask questions about your models. So this is using OpenAI in the backend, and it's calling the APIs from OpenAI in order to give you the answer. Similarly, we have another implementation for PowerSensor. PowerSensor is one of the DSS startups, and they provide an IoT device to help homeowners manage their electricity better. And they have a relatively small support team, and they want to minimize the support calls. So they came up with this chatbot using RAG, if you like, that is implemented on SageMaker, so Amazon SageMaker and Jumpstart, and it is using FLAN T5 model and mini LLM for converting text to embedding. So I quickly show a demo of that. So this is an example of this is actually the implementation for PowerSensor. You might go and ask what is PowerSensor. And as you can see, there is a bit of lag, and that's because these models are pretty big. So that's something to have in mind. So it goes and basically searches using the vector database in the backend. It goes and finds the relevant information, and it gives you the answers and where it has found the answer from. So this is the answer, and it's actually pretty good, as you can see, and it even tells you where you can find the content that it gave you. So another example is, how can I install PowerSensor? So you get the idea. I move on with the interest of time, but as you can see, again, something to have in mind is that these models are a little bit slow to respond. I say let's move on due to time, but it will give you the answer shortly, as you can see. Right. So next. So next is DataRock. So DataRock is also another DSS startup, and they provide machine learning powered platforms that help geologists with decision-making throughout the exploration and mining process. What we've seen in practice is that some of these rocks have some texture on them, and these confuse the models that are used, the predictive models that are used in the pipeline. So we came up with a solution where you pass these models, these rock photos to these models, and it goes and tries to smoothen the texture on them in such a way that the cracks are still preserved. And this is something that is important. So for this, we used an edge-preserving image smoothing GAN. And as you can see, we fine-tuned this model, and of course, it worked really well in practice. And with a very small amount of data, we could get this to work for, I think it was about 10 images or so. Another example is Creep. So Creep Creative, they provide marketing services for real estate, and providing high-quality images is critical for their service. And what they do is that, in this case, the real estate photographers take images of properties, and then these images are manually corrected to improve lighting and improve how the sky looks like, and they remove their reflections on the windows, and so on and so forth. So we experimented with Gen AI for this problem. We started with Stable Diffusion first, and we saw that basically stable diffusions were very expensive to train, and they required a lot of data for this specific task, and they were a bit more too creative. So we moved away from those, and we used a slightly simpler model called Pix2Pix, which is a specific type of GAN. And after fine-tuning on their data, which were about 30,000 pairs of images before and after correction, we could get this model to work really well. So these are the results of the models that you can see. And as you can see, as an example, in this example, it has learned to even correct the sky and make it look much nicer than the actual image. And that's the power of Gen AI, actually, that it can learn such things and do such tasks for you. So a few take-home messages. Model size is important, so you might want to be careful. The cost of infrastructure might be expensive, so you might want to use different techniques or model sizes. Sometimes what cloud providers provide in your region might be limiting what you can do, and it might impact the model that you might choose. When it comes to choosing these models, whether you are using an open source model or a proprietary model is important. Depending on your data, you might have some PII data that you don't want to send to other providers like OpenAI. So privacy becomes important in this case. And of course, the tunability of these models and the performance is important. And if you have a data set and you have some machine learning knowledge, you'd better, I think you will end up in the tuning and RLHF phase at some point in order to get a very good answers. With that, I'll hand it back to Marc.
Thanks, Shahin. I'm just conscious of time at the moment. So let me just share my screen. We'll start taking questions. We might only have room for one or two, so I'll just go to the top of the list. They're looking at Slido. The first question is from Tim. Hello, do you have any statistics on how quantization can reduce the precision accuracy? Shahin, that's one for you, I'd imagine.
Yeah, that's an interesting question. I think we've never benchmarked it for a specific problem, but you can use quantization aware training even to start with, or when you do fine tuning, which basically when you do that, you don't lose much accuracy. So that's actually a very good technique. But post-training quantization usually results in slightly worse performance. But I can't give you a number, unfortunately, because we haven't benchmarked that.
Okay, look, just really conscious of time because we've got 1 minute to 1:30. There's a bunch of interesting questions being asked here. We'll address them and return that to everybody. We might actually, as part of sharing the presentation, we might also give you all a link to our Slack channel, Slack DS community Slack channel, so you can ask us anything there as well. You know, you might have some questions that might have been sparked as you know, during the week or later down the track. One thing I do want to close with is to thank everybody for their time today. There was a lot that we did go through, but we do know there's plenty to navigate out there. So we'd like to offer everyone a complimentary workshop around generative AI, irrespective of where you might be in your journey. If you're still unsure about where to apply it, where it's the right for your business or a particular problem that you want to solve. Of course, we want to point it at the right problems, as we've mentioned many times in the past. Happy to help you through ideation sessions, for example. If you've started experimenting and want to move up that chain, I guess, that Shahin described around performance, we can help you through some strategies around that as well. So if you can click on or scan that QR code, that'll give you a link to sign up for that as well. So again, thank you everybody for your time, and thank you for sharing your lunchtime with us.